I can see now.
Okay. Can you okay, you can see now?
Yeah, I can see this. Thank you.
Okay. So we'll again quickly go through whatever I hope everybody else and I just want to confirm that everybody is able to see the screen now.
Yes. Someone raised hand.
Uh, Anybody who is not able to see the screen, please, can you please confirm? Uh, okay. I hope everyone can see. Okay, so Harika, what we did was we started with the recap of previous class. So these are just the important information. So I'll skip over here. So the references, the course outline. So today's and tomorrow's class will today's and the next class will conclude with module 2 over here. And then we'll start with module 3, which is the major focus of this particular course, the transmission line. So we have started with the recap. This is all that we have covered in the last class. And there's a question as well. Okay, so I'll take the question again. Okay, so we started with the last class we had dealt with the lossless condition. In the lossy part, we essentially focused that we have this sigma over here, and due to this presence of the sigma, the Helmholtz equation and the wave equation have been modified like this. And instead of using just k, we are now using gamma, which is the complex propagation constant, and it is expressed in this form alpha plus j beta, and this is the our wave equation, and its solution can be given by this form. And yeah, so essentially and solution, so this particular term is propagating in the negative direction, this is the positive direction. And this particular thing can be again written in time domain like this. So this is all known to you. And once we have the electric field over there, so we can just calculate the magnetic field by taking the curl. So if you know either of them, you must recall that in the Maxwell's equation we have the curl of electric field depending upon the magnetic field, and the curl of magnetic field depending upon the electric field, something like this. So yeah, so if you know either of them, you can calculate the other. Then we started with the case of good conductors, and the good conductors is what you can take either of these two conditions where this sigma is much greater than omega epsilon, or the imaginary part of the epsilon is more greater than the real part of the epsilon. So if you just take either of these two conditions in the lossy condition, you'll get will be able to derive all these equations. And we just quickly discuss this concept as well. So this is very standard thing you must know. We discussed the numerical that we covered in the last class, where we had to calculate the skin depth for the four metals. So I've shared the slides as well in the for the last class, and maybe you can take a uh, look on the last class slide, and you will be able to uh, follow. So this is the cheat sheet, and then we started with the general plane wave solutions. So there's a question that why have we assumed the solution of this particular form? So this is our basically the equation, right? So del square E is equal plus K naught square E equals 0, and then we expanded it to this form. And since E itself is of the form X, Y, and Z, uh, we are solving for Ex, Ey, and Ez separately. Solving for Ex, Ey, and Ez separately. Now, this is an assumption, and so this is more of a math thing than an electromagnetic thing. That we are assuming this particular solution, that the solution for this thing is given by uh, something of this form. And also, we are assuming that. So this is more sort of an assumption, and I myself am not very clear on why we are assuming this. So I like, can it be a function of sine z cos xy? So So the first part, why are we assuming it? I'll just like to answer it like the way that this is an assumption, and we are assuming that the EX field is only varying with in so the EX field is only varying in the X direction, and so the EX field is varying with X, Y, and Z. It's just that the this solution assumes the form that Fx is only varying in the X direction. And I'm not very sure of like why we are doing this. So, but this is, I think, yeah. So maybe going through the text will help. I'll look into this. But you're saying that can it be so the fx? Is it the question like this that can f be something of the form sine of z cos xy? Is it something? Is it what you're asking? Can f be of this form? Or are you asking that whether EX is of this particular form? I mean implicit function. Uh, Wait for you. Implicit function of three variables. So again, ma'am, I'm not sure why I'm not very clear with your answer. So maybe I'll come back to this in the next class. I'll look into this. But again, this is an assumption that we are taking that the EX is of the form fx, gy, and hz. And then once we have taken this assumption, and yeah, so this is the basically the key. Like after this assumption, it becomes really simple. Now then we substitute this back into this particular equation, and then we get this equation. The f by so this f double dash is basically the second derivative, d square by d. So this is the second derivative, and then we and again since we know that this particular partner is only dependent upon x, this is only dependent upon y, and this is only dependent on z, we can write them as equal to constant because they are not dependent on any each other. So essentially, we get these three equations, and then we can expand them back to the differential forms. And so we started with this PDE, partial differential equation, and now we have this ordinary differential equation. And the solution to this ordinary differential equation is known to us. And also by using these three equations and this particular equation over here, we can give a relationship between k naught and these three variables. Okay, so yes, ma'am, I'll make sure that I look into this. If I get anything which can throw more light on this, I'll share with the class. Maybe looking into math textbook can help. So I'll do that. Yes. Any more follow-up question, ma'am? Okay, maybe I'll pause over here and take any other question anybody else has. You can raise your hand or write in the chat. Can a magnetic field be conservative? Okay. Okay. Okay, I'll have to look into this again. I don't have a proper answer to this. So I assumed that it is non-conservative, but since you're asking that can it be conservative or not, I'll have to look into this. I believe it is non-conservative, but if any such cases arise, I'm not sure. Yeah, very interesting questions. Very answers to them will definitely help the class. Thank you, ma'am. And any other question? Any other question, ma'am? Any follow-up question from whatever we have discussed now? Can we measure the magnetic vector potential? Okay, in this particular course, we have not yet discussed the vector potential part, but again, since we only introduce the vector potential to solve the Maxwell's equation in a convenient way, I'm not sure whether we have tried to measure it or not. So this vector potential is usually introduced to help us instead of going through the integral part, we do differentiation and get the answer in a more convenient way. So I'll have to look into this whether we can measure this or not. But yeah, yes, and mostly in antennas, yeah, antennas and metamaterials, we introduce this to make make the solution more simple, the process. Because if we do not introduce them, we'll end up with integrals which are difficult. So yeah, I'll look into this whether can we measure this or not, and if even if we measure it, what do we use it for? Okay. Okay, so then we'll move to the next slide. So again, we solved this particular equation for EX. We change this PD into three ODEs. We have the solution which looks of this particular form, and finally, by using the substitution and things, we have the solution to EX as A e power minus JKR, where A is some arbitrary constant. And this A's value is usually determined by the boundary conditions and the source. Now, once we have like, so these are the steps. So we started this, and then we had the three differential equations and got the solution for EX. And similarly, similar treatment will help us get the solutions for EX and EY. And the final solution can be written of this form, where E naught is A, B, and in terms of A, B, and C. So yeah, this is the final solution for this particular equation. Yeah, sorry, this equation over here, that way from where we started. So solution to this can be given by this particular form. And now once we had the solution, taking a simple divergence of this particular solution gives us this equation over here, k dot E naught equals 0. So basically this says that for a plane wave, we do not have any electric field component in the direction of the propagation of the wave. So if the wave is propagating in the z direction, we will not will the Ez will be equal to 0. Now, a similar. So once we have found out the electric field, taking its curl and dividing it by this constants over here, we can find out the magnetic field. Now, solving for this, we get the magnetic field as n cross E. And now, since we know that if we write A is equals to B cross C, so we know that A is perpendicular to B and A is perpendicular to C as well. So since what we are saying that H is perpendicular to N. So again, so if the wave is propagating in Z direction, the HZ will also be 0. So essentially, this means that the plane waves for plane waves, we do not have any electric or magnetic field component in the direction of the propagation. So this is a diagram which shows, so if the electric field is in this direction, the magnetic field will be perpendicular to the electric field, and both of them will be perpendicular to the direction of the propagation. In last class also, we also looked at the circularly polarized plane waves, very important in antennas again. So right, up till now we were looking at just EX or EY. So if when we say that, so we basically are saying that electric field has components in EX, EY, and EZ on all these cases. And for plane waves, we saw that if the wave is propagated in Z direction, this is equal to 0. So the E field can be given in terms of EX or EY, EX and EY. And if you take a particular condition where so this EX or E1 is equals to J times E2, and both of them are equal to an value E naught. So the electric field is given by the in such a way, in this form. We can we can see that if we write it in the time domain, the electric field is essential. The electric field vector is essentially changing with both time and space. Similarly, in both time and space. Just a second. And now, since we know that the vector, the electric field vector is changing in both time and space, we can trace the vector's change of angle by finding out this particular angle phi as omega t. So we have come to know that this electric field vector, which is sometimes at Ex and sometimes at Ey, is rotating at an angle with this particular speed omega. So this particular angle is changing as omega t. So with if you take derivative with time, so d phi by dt will result in omega. So basically, this at omega speed, this is changing. So if we try to trace that particular vector, we will see that the vector is making a circle. So the electric field vector, which is rotating at omega angular speed, will trace a circle. Now, so this is why we call them a circularly polarized wave. That is because the polarization is not only fixed. That is it EX or EY? It is essentially something which is tracing a circle in the space. And we saw the two different cases where they could be either RHCP or LHCPs, that is right hand circularly polarized or left hand circularly polarized. So essentially, RHCP is one in which if you take your right hand and your thumb points in the direction of propagation, your the rest of the four fingers will trace the direction of the electric field vector. And similarly, in the LHCP, your left hand will be used, and you will have your thumb will point in the direction of the propagation, and your rest of the fingers will trace the direction of the electric field vector. So that's all we covered in the last class. So we'll start over here today. We'll start with energy and power. So maybe I'll pause over here and take any questions that you had from the previous class or what we discussed now. Okay. There's a question. Suppose we have a pure inductor in a circuit. Will it have any displacement current? So the pure inductor will Okay, I don't think I have an answer to this. I'll look again. Sorry, ma'am. I'll look. I'll have to look into this. Okay. Any questions from what we have discussed till now? Okay. Otherwise, we can start with today's the material that we have to cover today. Okay. So, so any electromagnetic source will have any electromagnetic energy source sets up electric and magnetic fields around it, which stores energy and can carry power through it. So, and this particular energy may be transmitted through the media in which the source is there, be or may be dissipated as loss. In and this particular energy so this is more sort of a high school uh, or electromagnetic. So this derivations maybe you can look into this. So we won't discuss how we got over here. So anyways, so this for a sinusoidal case, the time average stored energy in a volume is given as over here. So there's something wrong with my pencil over here. So the time averaged stored energy in a volume is given by this particular relationship, and similarly, similarly for magnetic field, they are so this is for an electric field, and this is for a magnetic field. And in case of a simple lossless homogeneous isotropic linear media, so this all this things basically make the epsilon as a scalar, real scalar constant. So this particular this d can be written in terms of epsilon e, and this epsilon, since it's scalar, this will come outside of the integral. And similarly, if the media is simple, so the mu will also become real and scalar, and this b, which can be written as mu h, can be replaced, and this mu will come outside of this integral. So essentially, we are saying that for a simple media, we can give the energy, this time average to electric and magnetic energy by these two equations. Now, there's this popular thing known as the Poynting theorem. I hope everybody is aware of this. We'll just quickly look at it. This Poynting theorem is the relationship of the and actually gives information about the energy conservation for the electromagnetic fields and sources. So if there is a source and the energy is leaving a particular volume or entering the volume, or it is getting dissipated in the volumes, all this information is given by this theorem, the Poynting theorem. So if you have an electric source current as Gs and the conduction current as sigma E, so the total current density is given by J equals Js plus sigma E. Now, again, so if we so this particular step is very important. So what we do is we take the Maxwell's curls equation, and the curl equation for E is multiplied by H conjugate, and the the curl equation for magnetic field is multiplied by the electric field. So so we take the first the curl of this second equation, and then we multiply it with the electric field. So what do we get is something of this form. So H conjugate multiplied by the curl of electric field, and E field multiplied by the conjugate of the second equation. So this all these terms, no need to worry. There are simple mathematics. If you multiply, then you will get these terms. Do not worry about them. So over here, the MS over here is the magnetic source current. And then again, using this particular vector identity, you don't need to recall this. So these are all present in the appendix of Mozart. May you take a printout and keep it with you. It will help you in solving questions. So using this vector identity, if you take the divergence of E cross H conjugate, you can write in terms of H conjugate in this term and E times this term. So you can substitute. So you have already calculated these over here, and you can substitute them over here, and we'll get this particular equation. So nothing much, just multiplication, addition, and simplification. That's all, and you'll end up with something looking like this. Now, so again, we started with the Maxwell's curves equation over here. We use this particular value and multiply it with the conjugates. And by doing so, we use this particular vector identity, and we achieved this particular equation. Now, what we do is we integrate it over a volume V. So if so, our area of concern looks something like this. So this is the volume V, and its surface area is given by some S, and we have this JS and MS as the sources and inside the the JS and MS are basically the electric current and the magnetic current on the surface of this particular volume, and this volume has been characterized by mu epsilon and sigma, and the outside is basically mu naught epsilon naught and sigma is equal to 0, and we have the electric field and magnetic field inside, and this n is the normal vector of this anywhere on the surface. So anywhere on the surface, the n represents the normal vector outside the surface. So if we integrate it over volume and then use divergence theorem, so this integration and so volume, and again this integration for over here, and we use the integrated volume, and this particular thing will then change from volume integral to surface integral by using divergence theorem. So this part changes over here, and this remains the same. So this particular thing, each of them is being integrated in volume. Okay, so we started. So in the previous slide, we started from here, and then we took us in a volume integral, and then changed from this volume integral to surface integral using the divergence theorem. And then we allow the media to be lossy. So that is, the epsilon can be represented as in a complex form, and mu can also be represented in a complex form. And we substitute this back over here. So we substitute this over here and over here. And after substitution and rearrangement, so we have this term over here. So this particular term comes from this. So this stays over here, and then we had this particular term this over here, and this term again remains the same. And this term is split into two parts, where we have the imaginary parts forming one term, and the real parts forming one term. So these three terms split into four terms, and we have one term over here. So this is math. Maybe maybe using a pen and paper will help you go through it better. Now, once we have already got this particular equation, this particular equation is this is the final Poynting's theorem. So this Poynting theorem was given by Sir J.H. Poynting, and this is basically power balance equation. So how this is the power balance equation, we'll see in the next slide. Okay, so before we'll discuss this and take questions. So let's look at the first term. So the first term over here represents the complex power being delivered by the sources JS and MS. So if you look closely, this is the we have JS and MS over here, and this particular term, this integral is basically the power delivered by the sources. Now, the second term over here, the first term basically on the right hand side of the equation. So we define this E cross H as S, and we call this Poynting vector. And this is essentially the complex power flow out of the closed surface. So this is basically representing the so we have the electric field inside this electric and magnetic field inside this particular volume, and any and the power which is flowing outside of this volume is being given by this particular Poynting theorem, and this particular Poynting vector. So this term is basically the power flowing outside. This is the power given by the sources. Now these the second and the third term on the right hand side are the basically the power dissipated in the volume, this particular volume, due to the conductivity, dielectric and magnetic losses. You can see this term comprises of the conductivity over here, and these terms comprise of the imaginary part of the epsilon and mu. And so basically the imaginary parts correspond to the losses, and so these two terms over here correspond to the power dissipated. So this is the power lost. So this power lost due to the conductivity, the permittivity, and the permeability. And this is also known as the Joule's law. Now, the last term is basically the amount of energy stored within the volume. So, if you recall this, and this looks very similar to this, and this particular term looks very similar to this. So these are essentially the same. If you if this is since this is scalar, if we take them scalar, they will come outside of this integral, and then you can write them in this particular form. So, we dissected the final equation. So this particular is the due to the source. This particular part is on the flowing outside. This is dissipated or lost, and this is stored. So each of the term corresponds to something, and so essentially, so this is saying that whatever power we had, it is either moving outside the volume, or being lost in the volume, or being stored in the volume. So this essentially, so this is the essence of the Poynting theorem. And we can then again, since we have already defined them using this um, values, we can write them in a very simple form like this, where the power of the source is related to the power moving outside, lost, or being stored inside the volume. And yeah, so this is the statement of the Poynting theorem, that it is the source power at the source is sum of the power being transmitted outside, or lost to heat, or being stored in the volume cell. That's it for the Poynting theorem. Okay, we'll pause over here. I covered the Poynting theorem and energy and power of the for the wave. We can maybe pause over here and take any questions that you might have. I believe this was clear. So this is something which is covered extensively in an electromagnetic theory course. Very important topic. So I hope that that's why this is not raising many questions to you. If you have any questions, you can then again come back. So meanwhile, we'll start with the power absorbed by a good conductor. So this is something which I found in Ozar. Okay, just a second. My stylus is creating some troubles today. Okay. So we in the last class we looked at good conductor. So which is not PEC. So this is we mostly to simplify our things we use PEC, where sigma is equals to this is sigma is infinite. But in most cases, this is limited. This is some fixed value, and we define good conductors at sigma much greater than epsilon omega, or epsilon double dash is much greater than epsilon dash. So this was the case of a good conductor, and since we have like there's a the sigma is not infinite, and this is some fixed value, we will have losses in the conductor. And now how do we calculate the power absorbed or the losses of this conductor? So we'll do some formulations over here. So if you take a look at this particular diagram, so this is one media, and this is your conductor. This particular part is your good conductor, and outside the conductor we have mu and epsilon. Inside the good conductor we have the sigma much greater than omega e, and we are taking this particular surface for the integral part. So this is the surface, and this n is the vector always pointing to inwards of this particular surface, and this S naught is the surface exposed to this particular this media, and this L and S is the surface inside the conductor. So if a field is incident from this direction, uh, and the field penetrates into Z greater than 0, so this is Z, and so this particular part is Z less than 0, and this is greater than 0. So the field is incident from this direction, and it penetrates inside. So we can give the power from the Poynting vector that we discussed. The real average power entering the conductor can be defined something like this. So the E cross H, and this is the n vector over here, which is in the Z direction. And the total surface is being given by S naught plus S. So S naught is the outside part, and the S is the inside part. Now what we can do is the contribution the contribution to this integral can be broken down into two parts, one from the S naught surface and one from the S surface. And the contribution of this S surface can be made zero by properly choosing this particular surface. So what we can do is, if we make this particular, so if the wave is incident is in this direction, and if you make this surface parallel to this to the direction of the propagation, thus which will essentially mean that this E vector. Uh, so E cross H is basically the direction of the propagation, right? So we can give this as K vector, and this, if we make this K vector in the perpendicular to n vector. So if we make this K perpendicular to n, what will end up is that this dot product will become equal to 0. So if this is the direction of K and this is the direction of n, or this is the direction of n, it will basically mean 0. And we know that this is a good conductor. Although so for PEC, the fields decay on the surfaces only, and for a good conductor, the fields decay very quickly. And if you take this particular distance to be very large, what will happen is that we will not have any fields leaving this particular from this particular surface. So fields at this surface will also be 0. So essentially, this will mean that all the okay, maybe I can clear this. So this will essentially mean that we do not have any contribution to this particular integral from these two boundaries, because K, this is the N and this is the K. So they are perpendicular to each other. And since the fields have already decayed in over here, so we do not have any fields leaving from this boundary. So we have made this contribution from this S as 0. So all will be left with this S naught. Yeah. So once we have made this as 0, to define the what we are left with this this power with only contribution from S naught. And over here again, using the vector identities, this Z dot E cross H can be written in this fashion, and we know that since Z is in the direction of the propagation, so we can replace this particular thing by over here, and we have N naught eta h dot h conjugate. So we have got this, and by substituting this over here, we can the power, average power can be given by this integral. So notice we had this real part over here. So instead, so this real has gone, and we have got this RS over here. So this RS is being given by the real part of the eta, which is again one for good conductors. We have derived this in the last class. So the real part is 1 plus 1 into this common thing over here, and this can be simplified to 1. And so we substituting the value, the skin depth of, we get this value. And this particular RS is known as surface resistance. Okay. So this is all from energy and power. So I will stop over here. We'll pause over here and take any questions that you might have. So I guess no questions from this. Yeah, this is pretty straightforward. What we were trying to do is trying to find out the losses, the power absorbed by a good conductor, and to in doing that process, what we did was we modified the surface and the volume which we are taking in such a way that the contribution for the uh, of the to the integral on the surface inside the good conductor became zero, and the only calculation that we had to do was on the surface of the conductor. So, so we'll start with reflection from a plane waves reflection from a media interface. So today we'll just take a very lenient look at it. The next class we will deal with this more clearly. Can anybody please confirm if my screen is still visible, and am I at slide number 29?
28, sir.
28. Okay. Okay, so not sure what's the issue here. Okay,
Now it's 29.
it's 29, right? Okay, so there's some lag going on. Okay, so we'll just take a very lenient look at it. So we won't spend much time. Anyways, today's class time is supposed to be up now. So we'll go through it quickly and take any questions you might have, or we can go through it again in the next class, and whatever questions you have in the next class as well. So essentially, what we are trying to say is that whenever we are looking at it, we won't be studying the waves only just in one medium, and it is bound that we will come across boundaries, and these boundaries will the waves will observe. Some of the waves will get transmitted, and some of them will be reflected back. So the relationship between the incident electric field, the reflected electric field, and the transmitted electric field is of concern to us right now. So over here, you can see that this is the free space over here, and then we have then we have a dielectric material over here, and its properties are given by epsilon mu and finite conductivity sigma, and yeah, so and this particular interface lies at z equals to 0. So we'll start right into this derivations again. So with no loss of generality, we can assume that the incident electric field vector is in the direction is oriented along the z along the x-axis, and it's propagating the z direction. So we are assuming that the wave is propagating the z direction, and the electric field vector is along the x-axis. And if you so if we assume this, we find out that the magnetic field is in the y direction. So after this assumption, we can simply write the incident fields for z less than 0, which is essentially this space over here, as ei x e naught e power minus jk k minus jk naught z. So this means that the wave is propagating in the positive z direction. And similarly, the magnetic field is given by this relationship, where n naught is the intrinsic impedance of the free space. So we've already discussed how do we get this. And for in the region Z, okay, so there's some maybe some mistake over here. So in the in region Z greater than 0, what we, if we have the reflection coefficient as gamma, we can give the reflected electric field and the reflected magnetic field by this particular relationship. So, so the wave since the wave is propagating in the positive z direction, the transmitted wave. Okay, sorry. So this is the reflected wave. So the reflected wave will then again propagate in the negative z direction. So that is why there's a change of this minus to plus over here. And similarly, so this and the reduced magnitude is being compensated by the reflection coefficient over here. And if you take the cross product, you'll find out from the the pointing vector is in the negative direction, showing that the direction of propagation of power is opposite to the incident field. Now, we've already seen that the incident electric field is given by as over here, and the reflected field is given by over here. Now, for the transmitted field for z greater than 0, if we take the transmission coefficient as t, you can see the direction of propagation for the transmitted field is the same of the incident field, and the magnitude is being compensated by the transmission coefficient t. And over here, if you can see the magnetic field is being calculated by by the sum eta, and this eta is basically the intrinsic impedance, which will be complex because the medium is lossy, and it is given as over here. So we have also seen this in one of the previous slides and previous classes. And the propagation constant inside this lossy medium is given by this particular equation over here. Now, we have already got the relationship between the incident electric field and the reflected so we have already found out these things: incident, reflected, and transmitted electric and magnetic fields. Now, the only things that we are left out with this gamma and this t. So this transmission and reflection coefficient are the unknowns to us. And since we are already aware of the boundary conditions from the previous classes, by using the boundary conditions for Ex and Hy at z equal to 0, by equating the tangential fields, we find out that this particular these equations can be related by this particular by given as by these two equations, and by simplifying these two equations, we can find out the gamma and the t, this reflection coefficient, the transmission coefficients in terms of the intrinsic impedance of the lossy media and the intrinsic impedance of the free space. Similarly, the transmission coefficients also are found out from these two terms only. Yeah, so that is all that we are covering today. And the next class will cover energy and power. So today we covered energy and power, and started with the plane wave reflection from a media interface. Uh, so maybe I'll pause over here, take any questions that you might have from what we discussed now. If not, we can close for today. Next class will cover plane wave reflection from the media interface that we've started today, and look at oblique incidence at dielectric interface. Okay. Any questions you have from today? Otherwise, we can end today's class. Okay. So we'll meet again on Monday. And yeah, meanwhile, maybe I'll put out some assignment and look into the questions asked by Sumatra ma'am. Sumatra ma'am. Okay, so I'll stop the recording.